We're continuing on with our design in Altium. In this video, we're going to be going over the boost converter. We're going to be building the boost converter, the switch for the boost converter. We're going to be talking about some practical features for when you're designing converters, especially DC-to-DC switching converters, but also for linear regulators. I mean, some of these principles apply to linear regulators too. We're going to be exploring a couple extra features of Altium as we go along. So I apologize to some people. The flow of this Altium tutorial is kind of, we're sort of doing it on the fly and we're kind of adding pieces here and there. So it's not quite as good as just plucking out a particular topic and just focusing on that topic. We're kind of learning as we go along, and I'm kind of adding functionality as we go along. If you do want to see specific topics, like if you want to see, how to create a part or how to do routing, a video dedicated to that, you can look elsewhere on my YouTube channel. I have a playlist of Altium tutorials that are an older version of Altium, but it still goes over most of the same stuff. So we're just going to move forward with the boost converter. And so I want to first talk a little bit about boost converters, what they do. We haven't gotten to this in class. We kind of have to get these PCBs out, so we haven't quite gotten to this. But the basic idea behind a boost converter is fairly straightforward. So looking at this diagram here, a boost converter is you have a supply, a voltage supply, and an inductor. And that inductor is connected to an output load through a diode. And it's fairly straightforward. If you think about the operation here, normally, if we didn't have this switch here, what would happen? You'd have voltage supply here, you would have some current flowing through this inductor, through the diode. The voltage here would be basically this voltage minus whatever the drop across the diode was. But the way a boost converter works is there's a switch here that allows you to effectively short this inductor. So what's happening is when you flip this switch and short it, current can't flow back through here because of this diode. So so whatever potential is across this capacitor, whatever potential is across the load, that current can't flow back. We can't drain this capacitor back through this closed switch. However, when we close this switch, by shorting this side of the inductor, we're essentially applying this entire voltage across the inductor. And as you know from inductor properties, that means you're going to start to have a change in current through the inductor proportional to the voltage and inversely proportional to the voltage and the inductance. So when we short this, when we flip this switch, we effectively start charging up the inductor. We start accumulating current in the inductor, and that's stored energy. So the energy stored in that inductor is Li squared, over 2. And then after we've stored up energy in this inductor in the form of current, if we then open the switch, what happens? Well, the current through an inductor can't change instantaneously, so what's going to happen is that current is then going to flow through this diode to the load. And the interesting thing is, even if this load voltage is higher than the voltage of the supply, this inductor is still going to drive current to that load. And so by adjusting how quickly you flip this switch and the duty cycle of this switch, you can actually produce a voltage at your output that is higher than the voltage at your input. And this is, this property, this idea of charging an inductor and then switching it and then using that stored energy to do something else, this exists all over the place. This is used in many different applications. And the neat thing about it is you can produce extremely high voltages with something like this without having the need for a transformer. You can produce very large voltages. So there's, I've seen circuits that use this to produce thousands of volts. You'll see there's many applications that need a small amount of current at a massive voltage to make something function, and you can typically use a boost converter like this for that. The limit for those extremes is the diode. The diode is going to break down at a certain. You got to make sure you have enough reverse voltage protection in the diode to handle those large voltages. But that's the basic operation. It's very simple. It's very neat. In practice, though, there's a lot of non-ideal things that happen because of this. One, we're generating a lot of noise. So we are rapidly changing a current. We're rapidly, dramatically changing the current through an inductor. So these dramatic shifts in current, often in a range of like megahertz range switching, generates a lot of noise. So it generates a lot of noise that not only do we have to deal with at the point of the boost converter, but sometimes anything nearby the boost converter, we have to take care of that. Another issue with boost converters is, by their nature, by basically fully cutting off current flow to the output and then switching current flow back on with this massive surge of current, these are noisy. These they're not noisy in terms of electromagnetic noise only. They're also noisy in terms of ripples. They tend to produce a lot of ripple at their output, which means that typically to smooth that out, we often have to have a very large capacitor here. And to smooth it out even more, which we'll get into when we talk about the sharp sensor, you can actually even kind of RC filter the output even further if you really need a nice, clean, smooth supply signal. So that's the basic operation of a boost converter. One thing I want to mention is this diode is, this boost converter requires an intelligent controller that can switch this switch as needed with the proper duty cycle, with a proper frequency as desired by the application to maintain a constant output voltage. So usually it takes a circuit that's sampling this output voltage and adjusting the duty cycle here accordingly. But this diode is non-ideal in the sense that we always have a forward voltage across this diode. We're going to be losing energy across this diode. What if we could replace this diode with a switch? So what if the controller, every time the controller shorted this, it opened the switch here, and every time it opened this, it closed the switch here. That would avoid the diode drop issue, right? That would avoid this problem with having this lost energy across the diode. But it requires a fast switching event, and it requires an intelligent system to do that switching. That's called a synchronous boost converter. So synchronous boost converters are a more efficient type of boost converter that basically do that. They take this, instead of having a diode here, they have a switch. There's another interesting thing about synchronous boost converters. Consider the case where this boost converter is off. So consider the case where the controller is turned off. It's not switching at all. What's going to happen here? Even when this is not operational, this output is going to see this input supply. And so with a boost converter, it can be very difficult with a normal boost converter to actually cut power to a circuit. You can't just turn off the boosting and cut power. You can't. There are DC to DC converters like linear regulators where you can do that. Where basically, if you cut them, they're just going to break the circuit, and they're just going to have no flow from the input to the output. It's not true of boost converters typically. Boost converters don't have that option. And buck converters, which we don't use for this lab, they do. Buck converters, they switch here. So you turn off the buck switching, it just opens the switch and it disconnects the output from the input. So one of the problems when we're using a boost converter commonly is we have to have, if we want to be able to power off our circuit, we have to have a way to physically cut the current flow. Physically cutting current flow can be tricky because, you might think, well, let's just use a switch. Let's just use a slide switch to just when the switch is switched, the current flows. When it's open, it's open. But in practice, it's very expensive to get switches that can switch a lot of current. So if you have a circuit that's powered by half an amp of current or even 100 milliamps of current, you might be paying a lot of money for a switch that's actually capable of handling that much current through its contacts. And even then, it's probably going to be non-ideal. So you generally don't want the resistance of that switch limiting this sort of boost circuit. You don't want to insert it there to limit that. So there are, if you're not using a synchronous boost and you're trying to cut power to your circuit, often that means you have to have a transistor here in line with this circuit, and you have to have a switch that basically opens or closes that transistor to physically cut power or cut current flow to the boost converter itself. But one advantage of using a synchronous boost converter is they normally are capable of actually cutting power. Because they actually use a switch here, they are usually capable of opening both of these switches up when they're disabled and fully cutting power to the output. Okay, that's what I wanted you to, that's the little lesson here on boost converters before we get into it. The boost converter we're using for, our lab is, look at this. I just Google search boost converter. I'm just trying to find a picture for explanation here. So the one that we're using is this TPS 61222. So a couple things to note. This is not a cheap boost converter in the sense that we can buy boost converters, especially from the Asian markets, for 5 to 10 cents each. This one from Texas Instruments costs closer to $1. It's maybe 70 cents or so. But there are some advantages to it. So this one is capable of operating with a very low input voltage. So this can boost up to, I believe, up to 3.3 volts using 0.7 volt input. That's a pretty good boost. A lot of systems can't touch small voltages like that. A lot of them have some voltage drop due to some sort of transistor at the input that doesn't really let them ever play games with small voltages. This one can. Which is kind of nifty. So, usually you're not going to be going down to 0.7, but you might be going down to 1.5 if you want to power something with a single, like a AA or AAA battery. You might be going down to, you might be having a 1.5 volt input, might be fairly common. For us, the input to our system is our 3.7 volt lithium polymer battery. So we're boosting 3.7, and our system voltage, our sharp air quality sensor requires a 5 volt supply. So we're just going to run everything off 5 volts. So we basically have to boost from 3.7 to 5 volts. And you might know with lithium polymer batteries, they're not really 3.7. That's sort of their nominal rated voltage. They really tend to be between 3.5 and 4.2 or 3.3 and 4.3 or so. So there's kind of a range of voltages they can have. And the boost converter will take care of that in the sense that the boost converter will dynamically adjust its behavior to maintain a constant output voltage. But one thing I want to show you when we look through the data sheet for this is minimum, so it's capable of 200 milliamps of output current, which will be fine for our application. Our sharp sensor averages about 20 milliamps, and as long as you're not going crazy with your op-amp circuits, they shouldn't be drawing 200 milliamps of current. We usually want to have headroom here anyway, so I wouldn't be comfortable if I only had a 200 milliamp limit and my circuit was 150 milliamps. I might sort of try to find a different way to do it, or try a different converter. A couple things. So looking at the schematic for this, looking at the simplified schematic here. So you have your input voltage, and this inductor goes into a terminal of the boost converter. Instead of, quite often you'll see, the inductor goes up across with a diode to the output, and then there's a little wire that comes in that allows you to kind of short that inductor. Here it's not. It's feeding directly in to the switching converter. And I believe this is synchronous. I didn't actually look into it, but it's synchronous rectification. So this is a synchronous boost converter, this is typically what you'll see. What this means is that internal to this chip, we have these two switches. So we have the switch that can short the other side of the inductor to ground, and we have the switch that can cut current flow from the output feeding back to the input. And so it's controlling both of those. And one of the features of this is looking at this enable pin here. This chip has an enable pin, which in this case, if we look down to the details here. So I stopped the video and cut it off because I found out something about this project. This circuit cannot use the enable pin to cut the current from the input to the output. It was something that my design that I did as an example design tried to do it. I assumed it did. It did not. I should have looked at the data sheet better. So I was gonna cover for it. I could have taken the video and gone back further and saved face, but I think it's, you got to take the rough with the smooth. When I screw up, I got to be honest about it. So I didn't look closely enough at this. One thing to note here is, so this transistor has all transistors like this have a body diode, which means that they're really only effective at cutting current in one direction. In this case, this transistor, for synchronous operation, we have these two transistors, the one at the top, one at the bottom. This one, which is designed to cut it's designed to cut current coming from V out back, right? We're trying not to drain the capacitor when we short the inductor. And it does not block current coming from the inductor to the output. That current can still flow through the body diode, which means this does not work. And if we're trying to, which means I spent 70 cents for everybody's part for nothing. But it is what it is. It's good. We can use this as a learning moment. We can make lemonade here. So we're gonna also add to this a MOSFET gated switch, which is a good thing to learn to see how to do. But for right now, let's piece together this boost converter. Let's piece together what little piece of dignity I have left. Couple things to note. Quite often, if you have good data sheets for parts, they'll give very specific details of what sort of components you should use to make this thing function correctly. You have to be very careful though, because just like if you ever buy some like food, you buy like Kraft mac and cheese, and they have like a recipe on the box. It's like, here's how to make, you know, super duper mac and cheese, and it'll always have like, use best food mayonnaise, or use Kraft mayonnaise, and use like all these other, they try to recommend parts that are from their partner brands. It's kind of the same way with these. They'll recommend parts, but you know, the manufacturer, the biggest thing is look at the parameters of the part. You don't have to look up this part number and buy it. It's very likely to be an expensive part. And who knows, you know, TI might use it. Some companies might find it worthwhile. You know, Coilcraft is a good company, but they're kind of pricey. But the biggest thing here is they want that the input capacitor, they want 10 microfarads. The output, they want 10 microfarads. They're recommending ceramic. So 10 microfarad ceramic capacitors are kind of the limit in 0603 capacitors. I forgot to mention in the last video, actually, not only did I forget to mention it, but I kind of left it. I didn't change the value. So this input decoupling capacitor was supposed to be 1 microfarad. So I guess I could change that now. But, you know, you got to be really careful with capacitor values, because just because you change a capacitor value, it's not like resistors. Resistors, pretty much you can find any resistor value in 0603, and your only real concern is how much power dissipation does it need. With capacitors, though, if you say, oh, I just want this capacitor to be a 220 microfarad capacitor, you are never going to find a 220 microfarad capacitor in 0603 footprint. That's going to be a very large, it's going to have to physically be a very large capacitor, so it just doesn't exist. So when it comes to just using capacitors and just changing the stated capacitor value, be very careful to make sure that it's something that actually exists. We do have 10 microfarad 0603 capacitors, which we could use for this. But one thing to note, these are 6.3 volt rated. That's about the limit in 0603. So you're not going to be able to find you're probably not going to be able to find a 10 volt rated 0603 10 microfarad ceramic capacitor. It's just, I haven't seen it. I don't think it really, or you know, it's certainly not 15, right? But so knowing the voltage rating for the capacitor, knowing the capacitance value, knowing the footprint, you have to make sure that all of these things exist when you're picking your part for the design. If you need something that's other than this, that's fine. You can get it, but you just gotta, you know, you gotta make sure you're picking the right part when using the Altium software. Another thing is, these are X5R ceramic capacitors. So X7R is generally a higher performing dielectric material. X5R is sort of the little lower performing, but I only see these compact capacitors exist with X5R. I don't know why. I don't know if that's a proper. I don't know why that is. But no, there's a difference between X5R and X7R, and there's different dielectric materials that give you different performance with temperature, different performance with voltage, things like that. So it's, you know, that's beyond the scope of this class, but it's just something to keep in mind. So this is normally when you have a boost regulator, the output is going to have a little resistor divider that connects to a feedback terminal. And so, and normally if you were this boost regulator, you don't generally know what your output voltage is. All you know is the output at your feedback pin. And so normally it's going to be something like, if you're designing a boost regulator, you say, we're going to keep changing, we're going to increase the duty cycle until that feedback pin reads 1.1 volts or 1.4 volts or 0.9 volts or whatever the feedback pin needs to read. And then it's up to the designer to pick a set of resistors, to pick a resistor divider that produces that voltage with the desired output voltage. And another thing to note is this feedback path is very sensitive. So remember what I said, when we're switching this inductor, we get a lot of noise. And if we have a big giant loop made by this resistive feedback network, especially if this is a big resistance here and it's a big giant loop, we're going to pick up a lot of noise, and it could create astable operations. It could create unstable operation in our boost converter. So feedback paths, if you have them, should be tight. Always look to see, sometimes they want a small capacitance over one of these resistors. To smooth it out a little bit to maintain stability. But the part that we're using for this is actually the TPS 61222. And so if we look at the 61222, well, come on. It's gonna be an embarrassing wandering. There we go. The 61222 is a fixed 5 volt output. So that's what we want. We want 5 volts output. This one is fixed, which means that that resistor divider exists inside the part. So, or effectively, right? So the part internally samples the output and does whatever division is needed internally to maintain an output of 5 volts. So something to keep in mind. So we're basically not going to have to do this resistor divider. So when we look at the feedback pin is probably going to be useless for us. But it is something to look into in terms of what you need to do to the feedback pin if you're using this different part. So I'm going to look through the data sheet really quick. Yeah, it must be connected to Vout at fixed output voltage version. So it's definitely something that we need to know here. Okay, so let's go back to, we've kind of spent probably way too much time looking at that data sheet. Let's go back to our components. Go back to our class components. So we can find in here boost regulator. Yeah, this is the part. And we can place this. Hit escape. Now, we had this part here. What if we didn't have it? What if we knew this is the part we wanted? We'd looked on DigiKey, we'd searched around, we'd said, okay, this TI part, we hadn't noticed that it doesn't block current flow. And we said, this is the part we want, but we didn't have it in the library. Well, you could make your own part, and I don't go over that in this class. You can find videos on my channel that do that. But if we didn't have it, we can do this manufacturer part search. And this was called, in previous versions of Altium, this was the Explorer, was where you would find this. And in previous versions before that, it was like library search. There was another name for it for earlier versions, like 4 or 5 years ago. But we can try to find this part. So if we search for this and we do TPS 61222 DCT, I don't know what the T was. Looks like it found this part. So I found a couple of them. So this one's from a UK supplier. So we can look at the models for this. Does this look the same? This looks suspiciously the same. I don't know the T and the 6. We could go back and look at the data sheet, the difference between the T and the 6. CKT. What? Yeah, okay, I don't know. So the package marking should be CKT. I don't know. I don't know why it's labeled like that. But what I usually do, I always do a sanity check, and I like physically check the footprint that gets produced. But if we wanted to, we could add this. So if we wanted to, we could find this part through DigiKey. The biggest thing to note when you're picking a part, especially from the DigiKey library, is they have a variety of footprint densities. So these are, if you're looking at the part here, you look really closely at those gold pads. See how the gold pads are really long here? And they're medium here, and they're very short here. These are referring to different densities of footprints. So if you're doing a design, let's say you're working for a company and you're trying to fit a really big, complicated circuit in a very small space, you're probably going to want to do a high density design, which means when you have a part, you're going to want fairly small pads for it. You're going to want to have fairly thin, you're not going to want to take up a bunch of space with these big long pads. Why would we want big long pads like this? We want them because it's easier to get a soldering iron on them. We also want them because typically in a reflow process, these longer pads are more likely to get to properly reflow than the smaller pads. But companies that, nowadays with the high density pads, most companies can, and they do sort of vapor phase reflows and things like that. They can usually do a pretty good job of getting proper reflow even with the small ones. So it's kind of a matter of preference. For us, we're going to be soldering these by hand. So we almost always would want the biggest pads we can find. So we would want to choose, in this case, this part number, and then we would place this part. Now, let me just see if there's a difference between these two. So just for now, let's just do annotation, annotate schematics quietly. So U2 was the one from our library, U3 was the one from the vault. And update the PCB document. So I'm just going to see if there's a difference here. Huh. Yeah, it looked like our footprint was sort of more of a smaller density than this one. Huh, I think I almost like that. I think I almost like that one from the vault. Yep. So I just clicked a part and deleted it. With Altium, if ever I'm deleting a part in a schematic, I always like to immediately update the board, because what can happen is if you have a part in a schematic and you delete it and say you swap it out with another part and then you try to update the schematic, Altium flips out. So Altium does not like that, because what Altium had done is it had created a bunch of signals. Even if you hadn't labeled the path, it had created a bunch of signals, and it knew, okay, this signal was connected to this pin of this part. When you remove that part and then put a new part in, and you didn't tell Altium in the middle that there was this part swap happening, sometimes it kind of throws a fit, because it says, okay, this signal used to be connected to this pin of this part, now it's connected to this pin of this part. Something happened. I'm not expecting this. So what I like to do is anytime I remove a part like that, I would update the PCB document again, and now Altium's saying, I'm going to remove that thing that you just deleted, and then I execute it, and then it just leaves this one here. So, okay. So, okay, but we got a bunch of other stuff we have to add to this. So, okay. Let's add the inductor. Oh, and now one thing also notice. So this thing was labeled U2. You know, I had labeled U2 and U3, and then I deleted U2. So now there's no U2. We just go U1 to U3. You can always, I think you can click apart and do. We can always manually unlabel this. So we can always manually put this back. And now, one thing to note is Altium says, yeah, it's U3, don't try to trick me, right? So, but if we re-annotate this, it should. Yeah, so now it's going to make it U2. So. Yeah, it doesn't like it's not connected, right? Okay, so now it made a U2. So we can always manually delete the annotation. You can also, there's functionality where you can reset schematic designators, reset duplicates. So I told you earlier, like if you're like shift clicking a part and moving it, sometimes Altium kind of like. If you're shift clicking to duplicate a part to reuse it and it's already numbered, Altium increments the number, which sometimes that incremented number already exists. And if that happens, just reset the duplicate schematic designators before you re-annotate, and it should be fine. But you can also back annotate the entire schematic. You can reset the designator. You know, there's lots of options for going back, for sort of redoing all this stuff. So. Okay, man, I've been talking too much. Hopefully you fast forwarded through all of that. If you're still here with me, thank you. Thanks for being here. So, all right, so let's start building. We want that inductor, so 4.7 microhenry inductor. We have one in the library, so we have one that I know we actually exist. So. Our VN's got to be V from the battery. Maybe what I want to do is just label this right now. And we're going to change. Let's call that VBAT. And then that will let me I'm just going to shift click this VBAT. here. Wire this up. So I am actually, because I realized I screwed up and got the wrong part, I am just going to tie the enable pin here. We are going to come back later and we're going to add a switch in here, but we'll get to that later. We need capacitors here. So did I have any capacitors? Oh, this is the big one that you're going to have to use later on. Nope, it looks not. We can go to components. We can go to miscellaneous devices and go to this cap semi, the 0603 one. So we can place, so yeah, again, 0603, you can get 0603 in 10 microfarads. So we can say this is 10 microfarads. What a lot of times you'll see though, a lot of designers are using tantalum capacitors a lot more. So typically, if you need a 10 microfarad, it would be very common to see designers use a tantalum capacitor. They are electrolytic capacitors. They are polarized, but they have some really good design properties. They have some really nice functionality across a range of temperatures, and for the most part, if they don't fail immediately, they tend not to fail. So they're different than a lot of other electrolytic capacitors in that respect. Let's add a tantalum capacitor, but first I want to show you how we can see what parts we actually have in stock. So we have a giant dry cabinet in the office, and there's a ton of parts in there. It's actually something that when I got here, I used my startup money. I bought $30,000 in parts for the dry cabinet, and that's really for you to use. That's there so that when students do development, they don't have to pay $7 shipping to get $4 of resistors, or to get 4 cents of resistors. So if you want to know what's in the parts cabinet, what you can do is you can go to, if you go to the R drive here, you can go into Smd Component Library, and you can find this spreadsheet called Smd Component Library. And in here is basically a listing of kind of everything we got. It's a listing of everything that's in that dry cabinet. Now here's the thing, it's not guaranteed that everything is in here. Some stuff can be out of stock and stuff like that. But this is sort of the master list of what we think is in there at any moment in time. And if we look at capacitors, right, it looks like we have ceramic. We do have a 10 microfarad, 6.3 volt ceramic capacitor. So we've got those. We also have these tantalum capacitors. So this tantalum capacitor is, this is the part number. So one thing I can do is, if I want to use that capacitor in my design, I can go to manufacturer part search. Close out of search. Add this one. Sometimes you get, oh yeah, look at that. So looky there. So I always like to scroll over and just make sure the prices are in US dollars. Now, one thing to note, Altium likes to use this manufacturer supplier parts list as a way to sort of, shuffle people off towards particular manufacturers and produce bill of materials that are easy and convenient and just buy it from these. So, again, just like with the white papers and data sheets that push you towards one company's products or another, just take it all with a grain of salt. If you find a part that you like, there's probably an equivalent part somewhere else. You could probably find, depending on what your needs are, how much validation you need for the part, you could maybe get them from an Asian brand or maybe not, to save a little bit of money. So, but for now, we have this part. We have a reel of 1,000 of them. So I'm just going to place this. I'm going to place the ceramic, and I'll just pop that there. I'm going to pop one at the output too. And then I'll also take this capacitor at the output. Okay. Got a lot of junk here. Okay, now it's very common to see input and output capacitors be one type of capacitor in parallel with another, and a lot of that's because different types of capacitors have different frequency response. Ceramic capacitors will typically have a better frequency response than electrolytic or than tantalum capacitors, and so a lot of times you'll put two capacitors in parallel with a smaller capacitor value with a higher frequency response used to filter out high frequency noise, and a bigger capacitor with lower frequency response used to filter out lower frequency noise. So, very often you'll see capacitors in parallel of different types. The other thing to note is if we do something like this, like the design that I'm showing here, we don't actually have to populate these when we do our final board. When we build our final board, if we say, the ceramics are fine by themselves, we don't need that extra tantalum, we can just leave it open, right? If you leave the pads open, unpopulated, it's not going to hurt anything. It's probably not going to hurt anything. And you'll see that a lot. If you look at if you crack open a piece of electronics and pull out a circuit board, I guarantee you'll find dozens of components on the circuit board that are unpopulated. They're just missing. They're just empty copper just empty solder coated pads. And that's, this is a common thing in design. A lot of times if you're designing a board, you might say, well, maybe when we get to testing this, we're going to find we need to add something here. I might as well put the footprint for it now, knowing I'll just leave it unpopulated if I don't need it. And and then after you go through the design process, if you find out, no, it turns out we didn't need it, you're not going to go through another design revision to remove that unless you have to. So you're just going to leave it there, just leave it unpopulated. Normally what you'll do is you'll place a tag that says DNP. You'll normally place a do not populate tag on that part to tell whoever's assembling the design, hey, don't actually populate this, leave this out. So, okay. All right, so let's wire these things up a little bit more. Let's do a ground, some grounds here. Just sprinkling grounds everywhere we go. We needed to wire this like that. The feedback had to be wired to the output. That was the design requirement. Okay. Now here's the cool thing. Now this output is our 5 volts. So this output from this switch regulator should produce a nice clean 5 volts. So we can just label this right now as, we could call it VCC. I usually like to be more descriptive. So I would just call it 5V0, which is a nice way of saying this is a 5.0 volt supply. A lot of times you'll see that. They'll use the V as the decimal place to save space. So you'll see like 3V3 referring to a 3.3 volt supply, or 5V0 referring to a 5 volt supply, or 1V8 referring to a 1.8 volt supply. So right now this is looking pretty good as our switching circuit design. And I've said this before, I like to do my designs piece by piece. I like to do a part in the schematic, transfer it over to the board, get my little cluster. Anytime I have a nice little clustered piece of components, I'll break it down into parts in a division of labor thing. So let's annotate quietly. And then let's update PCB document. Uh-oh. Didn't like it anyway. So anytime I get a warning like that of we couldn't match something, I usually really double, triple check to make sure that my design is correct. So, and sometimes I like to do it again. I like to do differences detected but no ECO generated. Please review the project options. Yeah. Okay. Well, so we're just going to triple check to make sure this is all good. We're going to make sure that the design is all good. So. Okay, so again, with me, we can work on this part of the circuit sort of over in its own little part of the world over here. We don't need to, buddy it up next to this quite yet. We might want to, rotate it 90 degrees or something later on. So I always like to go back to the schematic. I like to go back and see, okay, inductor 1 is connected to the chip as are capacitors 4 and 5 connected to the input. Probably should label them. So the input inductor was connected to the input, and it's really critical with these typically to keep the inductor close. So we usually want to keep the inductor very close to the pins, as close as possible. Lay bridges across the top. I might just do this for now. So then the inputs were C4 and C5, so we know these capacitors are in parallel, so I might as well just put them in parallel now, and then just take them as a kit. That's weird. What's that ground? Between ground. VBAT 5V0. I don't like what is going on here. Oh yeah, 5 1 6 4 2 3. Now, sometimes when it starts to seem weird, when it's like, what are they doing? What's going on? Like, come on, what are they thinking? Sometimes it's helpful to go back to the data sheets, because a lot of times when there's stuff like that, they usually had some idea in mind when they were designing this of how they expected you to lay this thing out. And sometimes they'll show you their layout idea. Look at that. Look at what they did. That's exactly what they've got going on here. So they show the resistor divider, which we don't have. We're not going to have that resistor divider. They show the inductor next to the enable pin, and C1 and C2 on the edges here. So let's copy their design. I might as well even do the orientation there. It's not copying, right? It's not cheating. It's using the resources available to us. The output capacitor. So let's just do the input capacitor. Now our capacitors are quite a bit bigger than their capacitors, so we have to keep that in mind. Looks like it's going to work though. And then the output capacitors. Hey, all right, thanks, TI. Sometimes the massive corporate entity works in our favor here. So, and again, I don't usually like to get things too close. There's no real need for us to get these things too incredibly close. There's no reason not to keep things sort of tight, but there's no reason it has to be nutso. It doesn't have to be insane here. All right, I kind of like that. I kind of like that as a layout. I feel pretty good about that. One thing I am going to do is, right now I might as well get these labels all correct. So again, I'm going to find all the labels on my design that are still 60 mil. And so I got that. I just right-clicked that and did find similar objects. It's a very handy feature. I'm going to change these to 30. And 6. So now let's get these. See that? How I couldn't grab that U2, so I had to kind of keep clicking at it? That happens sometimes. Okay, now you might say, why did I do the C4, C5 sideways? I kind of wanted to squeeze them in here to use this real estate in here. These aren't really super well labeled, right? Because, which... but if we're actually piecing this together, we'll be able to see there's one capacitor here, one capacitor here. It's not going to be unclear to us which is which. So we're going to be able to see this. So, I'm not... It's not going to be ambiguous which capacitor is which when it's done like this. But... it's something to keep in mind. Keep in mind always, after you're done labeling it, you have to be able to see these labels, know where they are. I might even sneak that label in there. Keep in mind, we're not going to be able to see this label after the inductor is placed there, but after the inductor is placed there, we don't need to see that label, so it is what it is. All right, this one's a little asymmetric, so I'm going to, just for... All right, that looks pretty good. I'm feeling pretty good about this. Now keep this one off to the side here. Okay, now we can route this thing too. So, so we might as well route this while we're looking at it, while we know what it is. I always try to route at the top layer if I can. First thing I'm going to do is route this inductor, and that's a little too fat, but I want this thing. I do want this thing to be fat, because I want this to, you know, there's a lot of, we have to switch a lot of current. Inductors possibly, you know, this is probably the highest current path in our system here. So, so 16 mil looks like it's about close to the limit here. Okay. There's my other one. My other critical path is, I'll just run that across. This one, these were signals here, so I'm not too, I might make this 10 mil. Because again, these are just signals. And the grounds, you know, we want to do a good job with the grounds. We don't want to cheap out with the grounds. So let's do our grounds. It's probably overkill. It's feeling like overkill here. And then what was my size limit? It was like 16 mil. Yeah. Okay, and then you know, also this one. This is our output. Oops. So we kind of want this to be kind of fat there. Sometimes you mess stuff up and you just gotta just redo it. I'm going to be honest, that is looking pretty good for a boost converter. I'm feeling very good about this boost converter. I'm proud of myself. It's okay. It's not vanity. It's just pride. Maybe these should have been a little bit fatter here. Yes, probably. Just to be a little more consistent, these should maybe be a little bit bigger. Oh yeah, we can't do that. We can't. See, now it's throwing a fit, right? Because I just changed this wire to 30 mil, and now you see these little green no-no markings. That basically means I just created a violation, and the violation in this case was this copper got too close to this copper, so we violated the clearance rule. And so what I should do is like what I did before, is put a skinnier spout like that, connect it to a bigger. Yeah, there we go. That's looking better. Look at that. It's beautiful. Let's look at it in 3D view. Hit the 3 key. Oh, yes. Yes. Look at that. That's great. That is just great. Okay. All right. Feeling pretty good. Now, I usually, in 3D view, I like to look at the markings and make sure, yeah, okay, if I saw these U2, I know it's U2, C4 and C5, it's pretty clear which capacitor is which here. So, okay. So now this is our nice little module that we can just do whatever with. So we could move this, we could hit the space bar, and we could rotate it, you know, we could, if we wanted to kind of have this thing make a turn in our circuit. But, you know, the good thing is right now it's just a nice little kit. So one thing with designing these PCBs is if you're going with a low-cost fab, your board limit is about 100 millimeters by 100 millimeters. So I'm going to show you really quickly how to just, right now we have this giant board space. I'm going to show you how to just for right now, we'll eventually clean this up later, but just so we know how much room we have to work with, let's redefine our board shape to be 100 millimeters by 100 millimeters. So to do that, we can hit the 1 key. If you hit the 1 key, it takes you to the kind of board layer definition, you know, universe, right? This is like the Upside Down or whatever in that show with the kids in the 80s. I don't know. Somebody will. So if you do, design, you can do redefine board shape. So that lets you basically just draw a square that redefines your board shape. And usually with this, I like to hit G and set a really coarse, I like to set a really coarse limit for myself. But now look up at this top left corner. This top left corner gives you your dx and dy coordinates. Right now these are in mils, so mils are thousandths of an inch. So, so 100 millimeter by 100 millimeter is, I mean, that's close to 4 inches by 4 inches. If we want to be sure we're under 100 millimeters by 100 millimeters, we can hit the Q key. Hitting the Q key switches you to metric. So you can see when I hit Q again in that top left corner there, we go to imperial units, hit Q, now we're metric. So 71 point, so we can see once we get up to about 100 millimeters, 99.06, what is that? That's, yeah, 3.9 mil. So let's just do that. Let's call it, we'll give ourselves some breathing room here. And we'll go up here. Oh man, this is big. 99. Minus 99, hit escape, boom. Okay. Now, so this is how much room we have to work with. So if now that I redefined the board shape, I can hit 2. I can hit the 2 key to go back to the design. Look at all this space, right? Look how much room there is for activities here, right? We could, we're not going to use all this, and usually with most designs, you don't want everything you make to be this 4 inch by 4 inch board, but this tells us how much space we actually have to work with. So this is the actual, scope of our realm of possibilities here. And that just lets us know, just so we don't ever get too wild. We know how much space we have to work with. It's very easy to lose sight of perspective when you're doing these designs. You can be zoomed in on a design and you can think this is as big as the universe, but you're just zoomed in, right? It's easy to lose sense of scale. These are very small components, and so it's hard to keep perspective sometimes. But setting the board shape is a way to do it. It's a way to help. It's time to save. Oh boy, what did I do? So it's time to save all, and like I said, I like to make backup copies. So probably what I'll do is I'll go back to my project even, and I'll go send to compressed zip folder, all to. Right, so make another backup copy. Now, switching. I told you. I realized I screwed up. This circuit cannot cut power. So how do we cut power to this circuit? So if we want to have a ground all connected, if we want to have the grounds of everything all be the grounds, then it means we're going to have, if we want to cut power to a part of the circuit, we have to cut it on the high side. We have to cut the upper voltage. And if we want to cut voltage on the high side, what kind of switch do we need? Can we use NMOS or PMOS transistors to switch the high side? Or another way to say it is when you took digital logic, which type of transistor passes a good one, right? Passes a good high voltage. Do PMOS or NMOS pass a good one? Do you put PMOS on the top side of a inverter or an NMOS? PMOS, you put PMOS on the top side. What's the downside of using PMOS? PMOS has lower hole mobility. It typically has twice the junction resistance, but for this case, it's not going to be too big of a deal. So what we're going to have to do is, if we want to have a switch that cuts power to our circuit, and we don't want to pay for a switch that can handle all the current flowing through the circuit, which is kind of dangerous too. Like if that contact starts to go bad, you're going to have sparking and it can create issues. And so I don't like to have a lot of current flowing through switches unless I absolutely have to. So what we're going to do is we're going to use a switch to produce a signal to a transistor, and that transistor is going to do the actual switching. Okay, but we know if we want to switch on the high side, we need a PMOS. Let's go back to our library. Let's let's see what stuff John bought so we don't have to. So if we go back to the Smd Components Library, so MOSFET P-channel. So looking at this, we have one P-channel MOSFET. Ooh, 1.4 amp limit. That's probably going to be good. So we have one P-channel MOSFET that's, oh, this is a BSS84. This is more of a signal. This is more of a signal MOSFET. It's, 130 milliamps. This probably would work, but I don't want to push it, especially if we're switching at the input of a boost regulator. That boost regulator wants a very pure low resistance path to power. So let's use this one. Let's use this this chip here as our PMOS. So let's see if it exists. I know I don't have it in the components thing, but let's go back to manufacturer part search. Look at that. Is it the UK supplier? Nope. All right. How many of these did I buy? Look at that. I paid $217 for 1,000 of these things. So you're welcome. Oh no, why can't I add it? Oh no, why can't I add it? What's it doing? It's not letting me place it. Oh no, does it not exist? No footprint. No symbol. What? Okay, yeah, all right. This happens sometimes. It really wants us to buy this stuff through Octoport, doesn't it? Well, let's see what the alternatives were. Well, first of all, let's pull up the data sheet for this. Because the biggest thing is we want to make sure the footprint is correct. So pulling up the data sheet. Okay, so really quickly scanning this, it's an SOT23 package. That's a fairly standard package for this size MOSFET. The drain and source, okay, so this is the main thing. That little, so we have drain here, source, gate, looking at the top view. So if I find an equivalent, if I find another SOT23 transistor that has this footprint, it should be good. I should be able to copy this. But I always like to go back to the actual, once I actually have the finished board, I like to look and make sure that footprint is correct. So, oh, okay. So what was this one? It said FDN 358P. I don't know why it recommended that as an alternative, but let's just see if they got it. Okay, they got models here. So let's look at the data sheet for this one. Source drain gate. Source drain gate. Perfect. Is it SOT23? Super SOT3. God dang it. Why did they do that? Yeah, SOT23. Super SOT trademark. It's the same. It's a standard footprint. Those jerks. Okay. All right. So we're going to use this one. This is not actually the part we're going to use, but this has the same footprint, so we just have to know. So let's place that part. Okay. So here is one issue that's common with transistors. So this transistor, the gain source and the gate source and drain, it's easy to confuse these together, to confuse these. But what you should always go by is the body diode. So for instance, if we're trying to block, if we have current coming from the battery to our switching converter, and we want to block that current, There's no way to block that current with the transistor in this orientation because the body diode, you can see the direction of the body diode, current flowing in is then going to go unblocked to the output. So this part, if we want to actually use it to block current, has to be oriented the other way. So the source and drain have to be flipped, going from left to right at least, right? We could leave it as is and just wire it across. But to keep it clean, one thing you can do is you can select a part and you can do edit, move, you can do flip selected sheet symbol along y-axis. What? Why is it not doing it? What's going on here? It's not doing it. Well, we have other alternatives. We can just rotate it, I guess. That's weird. Huh. Okay. Well. Okay, so I guess we'll just rotate it because it's not wanting to play nice with flipping. But so the issue is, so we're going to basically use this transistor to cut power to cut power to our circuit with a switch, which means that we don't actually want, right now we have this label VBAT and this label VBAT. If we're cutting power, we don't want to have these be called the same thing. So one thing we can do is we can call this like switch bat, right? To say that this is the VBAT signal on the other side of the switch. And then on our switch, we can basically just say, well, let's just do the shift pull. Put VBAT on this side, switch bat on this side. And now, how do we gate this? Well, to gate this, we're going to use an actual switch. So we do have that component in the library. If we go to 320 parts schematic library, we have slide switch, horizontal, place the switch. So what we're going to do is we're going to have this switch. I'll just do it and then explain what I did later. Let's give ourselves some headroom here. Okay. So what I've done is basically this switch has a common and then two connectors. And the way these types of switches work is when the switch is slid in one direction, this pin is connected to the common. And when the switch is slid in the other direction, this pin is connected to the common. So what's happening now is when I slide this switch back and forth, in one case, the input to this PMOS is going to be grounded. And what does that mean? If we ground the input to the PMOS, it's going to turn the PMOS on, right? Because then the voltage of this gate is going to be less than the threshold voltage away from the VBAT, which is going to allow current to flow. And if the switch is in the other direction, this gate is going to be connected to VBAT, which means there's going to be, we're not going to have any, our gate voltage is going to be 0, which means it's going to be turned off, which means there's going to be no current flow. So this is how we're going to gate this circuit, basically. And this is actually kind of a standalone circuit. I probably should have. I kind of want to separate these now because they're two separate things. Yeah. Okay. So that's how that's sort of the proper way to switch the power. I know a lot of people would just sort of take VBAT, connect it here, take the common of the switch and connect it over here, and just have all the current run through the switch. That's usually just kind of a bad design practice, so I would recommend against that. And so now basically, if this switch is switched off, this is fully going to cut the power to the from the battery. So the battery is going to be fully disconnected from this other circuit through this transistor. So. Okay, that's done. That's enough designing stuff. Let's actually implement this in the circuit. So let's do design. Wow, let's save. Oops, what did I just do? Okay. So now you see we have this switch and the transistor. So I just want to check really quick that, all right, so this, physically this is my gate, is this pin. Maybe it makes sense if I rotate it a little more. So physically my gate is here. And then we have the source and drain here. Let's go back and check our actual, I think maybe it's on this browser. So this is the part we want. Gate, drain, source. Perfect. And the body diode, current flows from drain to source. So here, current can flow. Yes. So current, so the body diode, current flows this way, so switch, it could flow back from switch back to VBAT, which is fine. So I'm just doing a little sanity check on myself there. Yeah, one thing I didn't do though was I didn't check the density of this thing. So oh, here we go. There's A, B, and C. I probably should have done that one. I could still see it. I'm going to change that, and then I'm going to update the PCB and change the footprint and see if that looks a little better. Yeah, that looks a little better. I just gave myself some longer contacts, and when I'm soldering this manually, I don't hate the universe. So, okay, and let's check the 3D view of these. It looks, oh man, look at that! Look at that! It's beautiful. Somebody spent a lot of time at On Semiconductor doing that. Oh wait, but we have to remind ourselves we're not actually using that part. So let's just leave a little note for ourselves here. The actual part we wanted to use, sorry On Semiconductor, was this one. What did I do? That's not the proper way to do it, because we have all these settings that are all switched, but at least as far as the schematic goes, at least it's a reminder to us. That's what we're trying to do. All right, now let's actually implement that at the board. I think after this is done, I'm going to cut this off. We'll call this a video. And then in the video after this, we're going to have to start moving a little bit quicker. I've been going a little slow through these, so we're going to have to kind of start just doing stuff. So you'll probably be relieved. You're going to get to not hear me so much. All right, so let's make some space here. Switch can kind of go anywhere, I guess. See how I have the switch hanging off the edge here? That's kind of an important thing to have the switch hanging off the edge, because you gotta physically, your finger has to be able to push that thing. So it's always a good practice to have that thing. What's going on here? So one thing to note is the switch doesn't really matter. The switch is just a signal. So the connections routed to the switch, even if they're going through holes and stuff like that, nobody cares. But the transistor does matter. The transistor is, this thing has a lot of current flowing through it. So we do want to be, and my grid is way too coarse right now. Yeah, okay. Well, maybe it's time to just. It's time to just. Let's look here. Yeah, it's okay. Okay, so we're gonna have a nice fat pipe from VBAT to here, and the switch is there. You know, we might as well just piece this one. I think I am going to rotate this. I think I am going to have this thing make a turn here. Yeah, I'll do that. I kind of like that. Actually, I kind of want to make this even more compact. I don't need to. I don't know why I'm going crazy here. And again, these ones are just signals, so we're not too worried about these actually. Yeah, we're not too concerned about these. We do though want to get a nice ground signal over to here, so I'm tempted. And we could do ground plane. I think I've been trying to kind of avoid ground planes for this class. But let's snake this guy through here. So now again, these for now. These things going to the switch are just signals. That was one of the things we said about the switch was, the switch is just a signal. What are these blue things here? Those are holes. So the switch actually has two little plastic pegs that punch through the board. So there's holes here that mechanically keep the switch in place, keep it from breaking. So just something to keep in mind. Okay, so other than the ground, that's all connected. So now we have to do the ground, and I think what I'm going to do is this. you can click and pull. Altium is usually pretty good about giving you the ability to do stuff like this. My grid is still too coarse, so. No reason to have these unnecessarily close to each other, so. A little stub bit of copper here. Okay. Now I can pull this ground all the way around. So I'm just gonna take this ground connection and just slink it all the way over. Now, if I had to run that ground all the way over there like that anyway, I might as well move this. I'm going to hold down Shift to also select that. I might as well just move this whole thing down to the edge of that. Clean up this trace here. About that. Alright, and now looking at this, there's no reason to cut that so close. Right, we didn't have to get right up in that pad's business here. Alright. Pretty good. We're kind of keeping it on the top layer here. Oh, wait. Nope. We still have to get a signal to this guy. Oh, we got tons of room to work here now, though, so. Watch this. Break it in the middle. All right. Watch what I'm doing here. Some of this is me just being just trying to make everything look kind of nice here. But again, this is a signal ground, so this doesn't have to be a fat pipe here. Oh, 10 millimeter. So I don't like to cut it close. I don't like to cut, if I don't have to, I don't like to cut too close to pads, so. Okay, look at that. Didn't have to use the bottom. We routed our switch. Let's take a look in 3D. Oops, we got to exit routing by hitting escape. Hit 3. Looks pretty good, except for the annotation. So one thing is I just plop this switch right to where my positive sign was for my battery connector. was like, why is everything looking for? I'm still in metric. I'm still in metric. So I hit Q again to get out of that. So now I wasn't finding the text height. Okay, and then we're gonna switch these two. I might just put that over here. You know, I don't need both a plus and minus. It's kind of implied. So maybe I'll just do this one. I'll just do a big plus sign for this one. And I don't even need the negative. I know which one's plus, which one's minus. Okay. Q1. We got a lot of space down here. Switch one. Again, I can put it right down here. It doesn't, you know, once it's populated, I don't necessarily need to see it. That's not always true. Sometimes if there's like a failure, you want to be able to see it, but I'm not too worried. Check it in 3D. You know, let's pull this. We don't need to have this switch one be out there. Okay, now that we rotated this part, these are all goofed up. So I'm just hitting spacebar twice to flip these. So I click and hold. Oops. Click once and hold, and then double click the spacebar. How's it looking? Pretty good. Look at that. It's looking great. Okay. So, file. Save all. And let's do a design rule check. So again, we got those silk to solder mask clearance we don't care about. We have one silk to silk clearance issue, which again doesn't matter. Oh, between the yeah. So it's basically saying that this gap is too small, which is true. Which also doesn't matter, but if we do that. Yeah, now I got rid of it. Now we just have this. Yeah. Okay. All right, feeling pretty good. Oops, what happened here? Yeah, okay. Let's save it. Come back next time.